Alright, what's next? Geiger counter? Everyone likes Geiger counters. Well, it doesn't really get any more American than this. This is one of the basically two styles of the classic Cold War Geiger counter, which were built because what happens after a nuclear attack, basically. There was the other model, the survey meter model, that's a much higher range, and then this is a Geiger counter model. And inside of here should be the Geiger tube on this little probe here. With the window closed, it measures gamma, and then if you open the window, it's also supposed to be able to measure beta. These Geiger counter units were sort of the, I guess, less desirable ones in case of a nuclear attack because they were too sensitive. You wouldn't be able to do, surveying your city or something. This would just be swamped everywhere. If you want to do something like, measure your radium clocks or your lantern mantles or uranium beads, they were good for that. I mean, there's better resources out there than me that can tell you all about these things and their history. With this one, I just want to get it working. And I should be able to do that with the parts that are in this bag. Not all of them, but... Warning, prevent corrosion, remove all batteries when not in use. Well, unfortunately, whoever has stored this did not follow that advice. And so that's something we'll have to fix. But there's the schematic. And I also have the original manual, which has the schematic in it. I'll look at the bottom case first. It's just got some rust and battery corrosion. But one interesting thing is that it has the check source on it. So what you were supposed to do was, get the probe and hold it up against there to get your calibration. And it is still radioactive. Do you know what's worse than lead paint chips? Uranium paint chips. Or radium paint chips. Different manufacturers use different materials under these check sources. I should be able to use my spectrometer here to figure out exactly what it is. Because if it's uranium, it's probably still good. But this should keep whatever's in there from leaking out. Just a precaution. And now here's the case after a light wash with some soapy water and wire brushing the rust, and it's pretty clean now. I gave it a slight spray of deoxit, and that'll hopefully help any rust, stop any rust from forming until I decide to paint this one day. Alright, now we're on to the electronics. So this is just this one circuit board, but I'm gonna have to take off these corroded battery holders. I might replace these with double A's because a 60s D cell has roughly the same capacity as a modern AA battery. And it's been known that they work just fine. Ah, it's an O-ring. So I guess this is supposed to be waterproof. Look at how smooth that is as well. Here's the circuit board, and just like any other piece of electronics is sold, there's a few modern components we can put in here to make the thing hopefully operate a little bit more reliably. So this large 400 microfarad capacitor that smooths out the meter movement, I can replace with a modern 470 microfarad electrolytic. Then I can replace this selenium rectifier here that rectifies the high voltage with a modern silicon diode. This gas-filled voltage regulator tube, which regulates the 900 volts for the Geiger tube, can be replaced with a stack of Zener diodes. And just because I'm ordering parts, I'm going to replace these two high voltage disc capacitors with high voltage film capacitors. All the rest of the other components should probably be okay so long as nothing's actually broken. Alright, it may be time to test it. Now, I'm going to look for the high voltage. I'm not sure I have a meter that can measure that with enough high enough input impedance that it won't load it down. But the manual says you can use a 20,000 ohm per volt meter on the 5,000 volt range. And I just happen to have a meter like that right here. And for this, the red is the positive, the black is negative, and the blue is midway between the battery stack. Alright, well I think we're good to go here. I'm going to flip the knob here and we'll see what, if anything, happens. And look at that, something did happen. So what voltage is that? Alright, it took me a couple minutes to realize what it was I was looking at, but we are in fact set up correctly. So we're in the 5,000 volt range, and the 20,000 ohms per volt divider here. This divides the full scale by 2, so instead of a 5,000 being here, this is now 2,500. But if I then turn on the Geiger counter, we're at about 500 volts here, 1,000 volts is here. But I forgot to turn the adjustment for the high voltage. And if I do that, There's a sweet spot where it goes right up to 910 volts. If I can find it again. There it is. And we'll go in for a close-up right there on the meter. So first making sure that the 0 point is set correctly. There's a little screw you turn in the middle of the meter for that. It's now over where 1000 volts is, so this 100 is 1000 volts. And right about where the needle is, that would be 900 volts at that major tick mark. The next smaller one is 925, and we're looking for 910 plus or minus 10 volts per the manual. So as I just turn the adjustment pot here, you can see we never really go over about 920-ish. So we're right where we want to be. And that right there is around 920 volts. So that's within tolerance. That Zener stack I'm using is 3 270 volts and 1 100 volt for a total of 910 volts. But that's a 6% tolerance. So at least with the accuracy of this old meter, which hasn't been calibrated and I don't even know, that's probably as good as I'm going to get with the tools I have available. I am hearing a little bit of arcing every now and then. But, oh, it's gone. Well, we'll see how that goes once it's installed in the case. Something else that seems strange to me, I don't know why the original manufacturer didn't clean off all of this extra flux. You'd think with the high voltage and the super low current, I mean, flux can provide a high resistance path between two pins if it's touching both of them. So you'd think you'd want to clean that off, but I don't know, for some reason they didn't. Too much wire on the end? No, there isn't. I think the meter is loading it down on startup. So I shut it down, turn it on. It only gets to there, but then I disconnect the meter and reconnect it a couple times maybe. Yep, and there it is at the 900 volts it's supposed to be on. Now if that's the case, I will turn it around. We'll plug the tube back in and see if anything at all reads on the meter. Alright, so it's supposed to turn it to, I think, 10. Okay, so we're supposed to turn it on to about 10, x10, and let it sit there. It should stay at 0, and it is. And then if I bring the check source close, then nothing happens. I also got a set of fresh new batteries, just like the manual says. There we go. This value is wrong because the meter was lying down before, but I know it won't go above 910, so we should be okay there. Also cleaned up the headphone plug and connected that. I'll put this right by the camera. Now if this is working correctly, if I put the Geiger tube in, we should hear that characteristic Geiger counter clicking, because that only depends on the voltage in the tube. There's no calibration for that. If I take this bad tube, or that I suspect to be bad, and just touch it in there, as I insert and remove it, you can hear it clicking, but once it's all in, nothing happens. So this may very well be a shorted tube. Now I do have 2 tubes here that are supposed to be good, but the other thing about these is, well, a Geiger tube is a 2-terminal device, but there's 3 pins on here. So the far away pin is one of the terminals, and then one of these will be the other side. And depending on the manufacturer, it could be this one or this one, and the other one was disconnected. Likewise, in the socket here, only one of these is connected. And that also varied by manufacturer. So when they built it, they just used whichever was the correct pin for the tube that they had. Now, if it still doesn't work with one of these, what I'll do next is, as I've tried on the bad tube here, is just take a little piece of wire and wrap it around both of those pins, which is the accepted fix for this sort of thing. But we'll just try one of them and see what happens first of all. And already I'm hearing a click every now and then, which will be from background radiation. Let me get the check source. Ah, yes. So that is a working tube. Alright, let's try the other one. Yeah, there it is. Random click every now and then. I bring the check source. There is clicking. So, didn't have to do that pin swap thing after all. I think I'll use this tube as the main tube, just since it matches the color a little bit better. I believe this plastic sleeve is meant to be kept in place. So that means I can put this back on. Now another thing is that the if it's working correctly, the power draw of this should be 33 milliamps. The manual doesn't say where you put the amp meter in series. I just put it in front of the positive terminal, the red wire, and I get something more like 100 milliamps. But that's the only spot on the HV tuning potentiometer right here where I can consistently get that 910 volts. So for AA batteries, I don't think 100 milliamps is particularly high. One explanation for the high power draw is that one of these two transistors is getting a bit old. But these are germanium transistors, so I don't have an offhand replacement for them. But I mean, it's working. I guess I'll leave it like that for now. Now, the last thing to set is the scaling on this meter here, for which there is another calibration potentiometer right there. Now, this doesn't affect the rate of clicking that comes from the tube, because that's set by the tube geometry and the physics that goes on inside of there. But it does affect the scaling of the meter so that it reads the right value. And what you're supposed to do with that is first open the tube and put it on the check source like that. And then set this to the X10 range. And per the manual, we are supposed to see between 1.5 and 2.5 millirems per hour here, averaging to about 2. So I will try to set that to 2. Alright, so now all I have to do is make a battery cover, or a battery mounting thing, I should say. You know what, I am going to clean off that flux. All you need for that is just some isopropyl alcohol. Now for the batteries, I'm going to stick with AA's. I've made this little 3D printed holder here that holds 4 of them. That will go something like this onto 4 3D printed spacers. And I have just the separate springs, which will go in the ends there. And all that extra space I created in that box is a great place to store the extra tube and any parts we removed. Just until next time. You know what? Throw in a desiccant pack just for good measure. And lastly, I can put that cap back. Something like that. Now with the cover closed, you can hear the high voltage supply a little bit better. So there you go. We've cleaned up the battery corrosion, made a new battery holder, cleaned up the main board, replaced some of the aging components with modern ones, and experienced 900 volts of shocking power. I was going to say we also replaced the tube with a new one that's not broken. And it's now working once again, just in time for the next Cuban Missile Crisis. Happy 4th of July.